we are still dependent on the X509 certificate. That certificate is something like you need to go to the authority to get it certified, because not everyone can become an MNO, not everyone can become that identity. So the proof actually depends on the existence of this authority that you were provided. That is the 509 certificate. But to prove the validity of the certificates, we are going to use proof. So in the end, we are still dependent on the GSMA circulating all these certificates, but then we on our end are going to prove that it's actually valid or not.
Yeah. So instead, like right now, currently we have to basically disclose this certificate.
Correct. Yeah. Okay. Thank you.
Cool. Sorry, yeah. Okay, so the project that I'm working on is I'm calling it a self-actualization game based on Tamagotchis. So basically, you have this like little pet guy they have to take care of, but like the old Tamagotchi, it just had like little buttons on a mobile device that you played with, but this is like a modern Tamagotchi, so I'm using data from the real world from what you actually do to take care of your pet. So in order for your pet to go to sleep or have a meal or exercise, you have to go do it, and then I read data from your phone and then plug it into the game server, and then your Tamagotchi does it. But I obviously want to make them more private, so I don't have access to all of the data that you're doing about your life, like where you're going and who you're with and what you do, etc. So I'm looking to integrate zero-knowledge proofs to basically prove that you've done some action in the real world without actually revealing what that action is to me, so then your Tamagotchi can then kind of replicate it. So this is like an existing project that has already been going on. So for the first week of Invisible Garden, I actually just like wrote tests around all the cryptography that I was already using. So I use Ethereum wallets and signed messages as actual authentication for my API. So you don't have session keys, actually. You just use Ethereum signed messages to authenticate every request, including the main game actions that I wanted to verify. And so I basically just wrote a bunch of tests, just verifying that like the right signatures were being processed and the right messages were being signed within those signatures, and a whole bunch of boring testing stuff to actually verify that the inputs into my zero-knowledge proof were actually like the valid game data that I was hoping to be verified. So that's about what I spent the first week on. And then the second week, this is a mobile app, so I'm using React Native, and so there's very different kind of like computing environments between mobile apps and mobile devices and the servers and laptops that we're used to doing. So I spent not a lot of time, but a fair amount of time just like going through all the ZK libraries and JavaScript, making sure that I could actually import them into my project and compile them into the native app so that I can actually run proofs on my phone, which luckily the apps are mostly just math and not even code, so there's not that many dependency issues. So yeah, I've already integrated all the ZK libraries into my game, and I've compiled them onto an Android app so that I could actually generate proofs. And then what else have I been doing? I sort of tried to think through what exactly is like the cryptographic protocol in the math and the actual like equations and variables for the proof that I wanted to generate. So just to like start off, this is like the first time I've done math in a while, even though I'm a programmer, like real math. And so I wanted to prove for my proof just one specific game action, not like an abstract general thing that you did. So it's like an in real life game. So I have these like Jamoji cards. One of them is actually by the Ethereum PSE team, which has the baby Jub Jub curve on it. And so I've been integrating these cards as part of the actual game. So you actually have to get a signature from this card to do stuff. So I wanted to verify that someone had received this signature from a card, and also that that signature was part of some set of signatures that are like valid game action doers. And so, yeah, I've mostly been just like going through in a notebook, which is why I'm not showing it here, just like the equation of the cryptography protocol of what exact information do I need to give and provide, and certain inputs I want to keep secret. So how do I keep those secret? So you're not revealing who signed for you, which is what I'm trying to like hide with the zero knowledge proof. So yeah, that was another thing I did. I'm like working on the actual math to understand zero knowledge better, and then also to prove that the proof that I'm writing will actually do the things that I want it to do. Namely, keeping secret who is the person that like gave you the signature. Like, who did you actually meet is secret. You know that you met someone that's valid, but you don't know who they were. Which means I also have to hide the signature, because obviously the signature can then derive the address, and that address is associated with the player in the game. So I have to hide the message and also who signed it. So I might as well just go into the circuit now, because that's basically what I'm doing. So I'm using baby jub curves mostly just because Professor Guo said that it would be cool. So I figured that was like style points. And I'm seeing why it's style points is because it's kind of annoying to do in zero knowledge proofs, at least for Ethereum messages, because we use Kekak, which is apparently not like zero knowledge compatible or efficient. So I'm now doing all this weird stuff in my circuit to try to basically turn, or to prove in ECDSA signature without actually using Kekak, which Kekak is used in Ethereum stuff specifically. So because I'm using Ethereum wallets, I now have to kind of finagle some things if I also want to use the baby jub curve, which I figure I might as well. What, is that funny, the baby jub curve? It's just a thing? Yeah, okay. So yeah, basically right now I'm maybe like halfway through writing my circuit, which basically it takes the game command, the action that you are proving that you did, and then the signed message is a private input, and a public input is also like all the valid signers in the game that you're saying could have taken the action, and then basically prove that you have received this from someone. So you're proving the command that someone has like allowed you to do this thing, but you're hiding the actual signed messages and therefore also the signer, but you're proving that the signer that allowed you to do the thing is part of some set of signers. So right now I'm just deriving the signer from the signed message, which is a private input, and then matching that signer against the list of signers that have been provided within the circuit. And then right now, just kind of the problems I'm having are using the baby jub curve with also normal ECDSA stuff. So I could just not use baby jub, and this would basically be done already. But I've got a couple more weeks, so I might as well keep going. And then I just have to figure out how to actually like use the baby jub curve on this card, because I know it signs with like a normal curve or with like a normal wallet. But I don't know how to like activate the specific like baby jub signature. So those are like basically the two things I have left besides like actually integrating into my game. Yeah, which I think was like my last point. Generate, proof for the game association. So like this is all just my front end right now. And then I also have obviously my backend, my game server, which I'm trying to avoid with zero knowledge proof. So I'm trying to design the zero knowledge proof so it doesn't use a Merkle tree or a Merkle proof, for example, because that would make my game server like the central authority on like who is allowed to be sending these signatures or who's allowed to be inside of the Merkle tree. And I want this to be like an offline peer-to-peer game. And so I'm not using a Merkle proof because then you would need to know all the people that would be valid within that tree. And you as an individual player don't know everyone. You don't know the whole game state. You just know that I, as an individual player, have this valid game action, and you just want to prove to someone else that you have a valid action, or that it has been done, or you are going to do it, or whatever. So that's a little bit about the setup of why I'm doing things, and also why I don't have server code is because I'm trying to use zero knowledge proofs so that my server doesn't have access to this information. So I already have the function, which I haven't tested yet because I don't have the proof to run it against, or the circom circuit. But basically this takes the game action that you wanted to do and then basically generates the various inputs for the circom circuit, and then generates the proof using Snark.js, and then outputs whether or not that proof is valid or not. And then that would get used also within the app, not in my server, to prove to other players that, basically you've been allowed to play the game. And what else? That's about it. And then I'm planning on basically just taking this very simple proof, which I know the Jamoji team at PSE has something like this, so I've been like obviously looking at their code to see like how are they actually proving things and the baby jub and blah blah blah. So I picked an easy example that I know that there's kind of like test cases for us, just so I can like learn and actually understand the parts and whatever. And then the next component of this will be to prove actual data, like proving that you took 10,000 steps yesterday or whatever, and then sending that proof to my server. So yeah, that's what I've been doing at Invisible Garden. Cool. Any questions? Yeah.
What's
The
the playtest?
playtest? Yeah, you can install the game now. It's at, let's see if you can see the website here. Not really. app.genie.health. That's like way too small. Let's see. Do I have a QR code? I don't have a QR code. What would be the easiest way for me to share it with you? I can post it in Discord. Yeah, I'll do that right now.
I think you answered in the last statement, but I just wanted to confirm. So right now, the only action there is in the game is to have like the card.
That's the only action that I'm verifying with the zero knowledge proof right now. Yeah, but there's other actions right now, like that you've been pushing to your GitHub or that you've been going on steps.
It's just not.
Part of the proof.
Yeah, it's just not private.
Yeah, it's not private at all. Yeah, you're giving me all of your data right now, so I know like exactly when you've committed or when you went for a walk, or I know a lot of information basically. So it'd be better if I didn't have that, right? But right now I'm the only one that plays the game because I made the game for myself. So there's some other people that have their data, which is mostly my friends. But ideally it's not an issue at all, right? So trying to make it not an issue.
Do you want it to be social or just your portfolio?
Yeah, so that's kind of why I'm now doing this. Before it was like a personal private game where you're just playing with yourself. And then as part of Chiang Mai, I was talking to Edge City and some of the other pop-ups and they wanted to play. So then I built in a more social aspect where now anyone that has a Jamoji card, before it was just mine and I hard-coded my address in. But now anyone with a Jamoji card can start to create Tamagotchis and community Tamagotchis that people take care of. So that's kind of the social stuff that I'm trying to enable, which is also why I want to do the proofs like peer-to-peer and not through my game server, is because ideally the game starts becoming more and more like local hosted and more like social aspects. And right now you kind of need like a centralized database to do social features because then you have data about everyone. And then the more I can create the architecture to be more like natively peer-to-peer, then you can host more of your data yourself and then have more of those social features be zero knowledge based versus like through my server. Yeah.
After you're done, I want to show you something. I built something like this for myself.
Yeah. Sick.
It's just like Web2.
Yeah.
Everything is connected.
Yeah.
I think you might be interested.
Yeah, I mean, this is also Web2. Like I use API servers and like I talk to GitHub and Facebook and whatever. But I'm trying to make the game as like Web3 as possible, mostly from like a security and privacy perspective. So there's no on-chain component. But that's why I'm using zero knowledge proofs so that I can like verify game aspects of the game without having it to be on-chain. For sure. Thank you guys. So. Oh, sick.
Yeah, I think we just pass it around.
And yeah, just briefly go to the passport. Just look.
Damn, this looks weird. Jeez, this works. Ah, good enough. Alrighty. Yeah, so our team is called ZK Links.
Our team is called ZK Links. Basically, what we want to focus on is, if you've heard about Rust Links, it's an intro into Rust, the programming language, and we basically adopted kind of premise and basically want to build a better way for people to better get into ZK. The goal is mainly to educate developers about the implementation of ZK proofs. So this implies basically enabling to differentiate between different proving schemes, between commitment schemes, proving systems, and basically better understand what's kind of happening behind all the abstraction. This also implies kind of understanding the security assumptions that you make when you use certain proving schemes, and then also what kind of trade-offs the different proving systems do have. So to kind of do that, we have quite a big team, which is actually quite nice. It was initially a fork from Root's ZK Links repo, which we used as a foundation, which is also a fork from Rust Links. And we now have 7 contributors, which is nice because we can actually increase the width of different exercises that would be necessary. But most of us also work on a different project at the same time. So we're trying to go through person by person by person, just give a quick update from what we've been working on and what's kind of the intention behind that is. What I do want to show right now is that this is the repo. This is the ZK Links repo from which we're starting. So all of our updates will be merged within this main repo. So it's basically running open source with different kind of open contributors. And just to visualize how this works, oh god, let me see. Yeah, okay, so it's all happening within the terminal. So as a developer, you only really need to work within the terminal. Okay, let me see if I can make this work. Yeah, so basically all you only need to really work within here. You can go through different lists of exercises and then you can work on them. And now just for an example from my side, so I'm currently working on finite fields, where I'm basically adding different kind of exercises for finite fields, which people can then test themselves on and basically further the understanding of this specific aspect of ZK proofs. So we're just going to make a quick round. We have 2 minutes each.
2 minutes each, okay. I'm working on fast Fourier transforms. So I don't know what that is. So that's part of my research is learning about that and then figuring out what's the best way to actually explain that concept and why it's a useful concept and what it's used for within math and within cryptography and ZK. So yeah, I'm doing FFTs.
Can you show the slide? Yeah, thank you. Hi, for me, it is more on the focusing on the mechanics of the ZK Links itself. Usually, when you editing the code on anything, which is on the exercise, there is update. Like checking new one if it's correct or not. In this case, I am implementing the flow itself, mostly more on the aside from compiling the circuit, we also generating and verifying, checking that the circuit is really work on that exercise. Even though right now it's a little bit problem on the updating. Yeah, so we am more on polishing the US flow, making the user interface flow on the learning this thing much better. Thank you.
So I'm working on creating problems for mainly whatever we are studying. So we have a folder called ZK Protocol Basics. It is about all the problems. So I've created the how the discrete log works, and then there's a problem that why it is good, and then I'm gonna implement the Schnorr protocol and the Peterson. So whatever we are learning right now, I'm implementing them as a problem so people can learn it better.
Okay, so can you open the issues list? Yeah, I'm currently working on the IPA part, and actually Dr. Gore just gave some talk about it. And my first step is want to written it in Python first, and also there's a project, maybe you can open it. It's by Dr. Gore. It's implement some protocols in Python. So I will first implement the IPA in Python, and then I will go to the Rust part. And I have already finished the split and fold part, just lecture by Dr. Gore yesterday. Yeah, so anyone interested can check that out. Yeah.
Hi, I'm Ganil. I'll be creating some examples on Plonky 3. So it would be it will be depend upon. So how do you define your execution trace? How do you define your AS scripts? And how do you choose different hash fields for your program? And it would be a couple of examples, including Fibonacci, ECDSA. Digital signatures, etc. So yeah, I'll be creating some of these examples throughout the cohort.
Yeah, I'm Harold. So I'm working with JK on the finite field. So basically, my job is write some Python prototype with the field and group some examples. So like the users can feel the the little bit difference and some of the crucial features for those algebra structures. So that's it. Yeah.
Alrighty, so yeah, so we're still a big group, but I think we could even accept more contributors, to be honest. I think the whole idea is that as we're building our own projects and we learn more additional features or like things about ZKs, I think we just put that into practice and also allow others to kind of go through a nicer learning experience and yeah, just kind of also learn through it as well. So I think that's basically it. Thank you for listening. Yeah. Any questions? Pretty clear. Yeah. Alrighty, thank you.
ZK action.
Okay, so hello everyone. Yeah, today I will talk about our project. It's named Silent Beat, and my team is ZK Ocean. So for the discussion and hours, you can see here that we want to build a zero-bit Ocean platform that use Plonky Tree Toolkit. So for who don't know about zero-bit Ocean, it's a type of Ocean that the bidder can submit and bid without knowing each other amount. So we leverage we try to use ZKB to choose the highest bidder and without revealing the bid amount of each other. So our is ensure that the both privacy and fairness in the bidding process, and moreover we want our project will serve as a reference model to developer in the future that want to build the apps using Plonky Tree Toolkits and also ZKB. So let's dive into our architecture. You can see here that there are four main phases. The first phase is about the setup that the owner of the Ocean asset that create the Ocean. We are invoking the smart contract. And then in the bidding phase, the bidder that who want to choice the Ocean can deposit and also submit and bid, but the bid amount will be encrypted by the owner public key. And then after that, in the open phase, the owner now run the proofing service of chain and send to it the private key and decrypt the amount from all the bidders. And then the proving service will choose the winner, which is the one who have highest bid, and also generate the proof to prove that all of this process is true. And then finally, in the verify phase, the owner now can submit the winner and the proof into the smart contract. So that is the basic flow that we want to do in our project, and we have two main approaches. The first approach is that for the proving service we write in Rust and using Plonky Tree Toolkit. And for now, Plonky Tree is not complete yet. It just support FRI polynomial coming schemes and also stack. So what we have to do is about the proving service is that we have to define our constraints in stack and also generate our execution trace. So, and for the smart contract, we have to write the stack verifier on it. So, it's the first approach. And for the second approach, we write the logic code in Rust and then put it in the SB1. The SB1 is a ZKVM which use Blocky Tree toolkit, and yeah, so it's open source and verify any program that written in Rust. And for the verifier in smart contract, the SB1 already have, so we just use it. So yeah, so my team now already working on 2 Apache on parallel. So if we can finish that soon, we can make some benchmark of 2 Apache for this project. So okay, so that's all. Thank you. So, yeah.
How would something like a victory option work, where the second highest bidder, the winner plays the second highest bidder's amount? How would that work if everyone is your knowledge and you don't know how much anyone is?
Yeah, actually, you can. Here is back to our workflow that the proving service can decrypt the amount of bidders so that he can choose a winner because he decrypt it. So.
What if the amount that the winner pays is based on someone else's bid? Like you can prove that one person has the highest amount.
Yeah.
But how do you have them pay different amounts than what they did in the auction?
You mean that the one bidder can bid many times, right?
He's talking about a type of auction where the winner pays the second highest price, and the economic theory behind this is that this allows bidders to pick their most honest valuation.
So
basically, how do you?
Yeah.
Like, let's say I win.
Yeah.
And I can use a zero knowledge proof.
Yeah.
Prove that I won without showing the amount that I bid. But now I have to pay to actually receive the amount from the auction.
Yeah.
The item that's being auctioned.
Yeah.
But I don't pay what I bid. I paid what he bid.
Oh.
Right?
Yeah.
Yeah. Yeah. So.
Yeah. Actually, we the proof is generated by the owner, but not the bidder who wins. So the proof is generated by the owner and submit in the smart contract. So if the smart contract verify that, we review the winner too. So that so the smart contract will review the winner. So the winner can claim from the smart contract. Yeah.
So like the owner could put it into the proof that they submit to the smart contract what
Yeah.
the actual payment amount is.
Yeah. So.
Yeah, because every bidder does know how like the amount of the others, so there's no way that they can know that if they are a winner or not. So yeah, the one that the approval must be the winner.
So yeah.
What happens if there are more people bidding the same values?
Actually, we just like choose the first one who. Yeah.
This is abstract for this, and we are building like a prototype, so we cannot consider.
So any question?
I have another question.
Yeah.
You're building 2 approaches in parallel.
Yeah.
Why don't you focus on building
Just.
the fastest one first, and then
Yeah.
consider to build the other one?
Yeah, actually, these 2 approaches have some, minus points for it. The first one is, the first approach is that when we try to define our constraints and the execution trace with some hash function and encryption, so it is hard to define. And then, but if we come to approach 2, it's not. If we try to do the approach 2, we don't use the Blocky tree directly. So yeah, that's the trade-off between
Yes,
So-
what I'm asking is why don't you go through the second approach
So-
first?
Yeah.
And then consider if you need to go.
Okay.
Yeah, so because we in our team we have 4 people, so we decided that we would split them into like 2 smaller team with 2 people working on 2 team working on different approach. And because it's not like overlap,